Hi everyone, welcome back to CSM walkthroughs for EEC16B. This is week 3, and we are going over question 3, part C. Is it C? Yeah, part C for this video. Okay, for part C, we have a buffer joining the high pass filter and the low pass filter. If you are wondering why this is called the high pass, and this is called the low pass filter, just check the previous videos for part A and part B. But anyways, we now see how this circuit will behave. But first, we want the transfer function. Now, the transfer function for this one is doesn't require much calculations, because let's call this part V middle. Then we know that our V middle phasor is equal to the transfer function for the low pass filter times our Vn phasor. And here we know that our V out phasor is equal to the transfer function for our high pass filter times our V middle phasor, because V middle acts as a Vn for our high pass filter. So combining these equations, we get to the point where our V out phasor is equal to the high pass filter times so we plug this into our Vm phasor. And we end up with this equation. So we do the same thing where we divide both sides by Vn phasor, and we get V out over Vn equal to the product of the high pass filter transfer function and the transfer function for the low pass filter. So in the future, when you see a buffer, you don't need much calculation. You could just end up using the product of the two filters, of the transfer functions for the two filters. Next, we want the magnitude of the transfer function when omega approaches 0. So now we will use these values from above. So that just gives us 1 over 1 plus j omega RC 1 plus j omega RC equals times 1 over 1 plus j omega RC. So when we take the limit, then these go to 0, and we are left with 0. Because the numerator goes to 0 because 0 times 1 is 0, but the denominator doesn't go to 0. The denominator goes to 1 times 1, which is 1. So that means the whole thing goes to 0. And 0 has a magnitude of 0. Okay? So we see that the V out is equal to 0 for omega approaching 0. Next, we have our limit where omega goes to infinity. So that would just give us well, let's see. Both the numerator and the denominator goes to infinity. So we probably want to use the L'Hopital's rule again. So we use the L'Hopital's rule. Taking the derivative of the numerator with respect to omega is just JRC. Taking the derivative of the denominator gives us, so this is basically 1 plus j omega RC squared. So taking the derivative gives us 2 times 1 plus j omega RC times, by the chain rule, JRC. Now we notice that when we take omega to infinity, this goes to infinity. But this one is just a constant. So that would mean our denominator goes to infinity while our numerator doesn't. And that means our whole thing goes to 0. Well, isn't that weird? So that would again mean that our V out is 0 for omega that goes to infinity. But that is indeed expected, because we notice that our V input whatever frequency that our V input has, if it's a low frequency, then it won't be able to pass this part, this buffer. I mean, it won't be able to pass the low pass filter. So we will have a 0 voltage here. But so if we have a 0 input voltage for our high pass filter, we will of course have a 0 output voltage for our high pass filter, thus the whole cascaded filter. And if we have a high frequency, omega, coming into our low pass filter, it will go through the low pass filter. Okay, I messed it up, but you get the point. So it wouldn't go past the low pass filter if it's a high voltage. So I will use, so remember the orange one, I will use the orange one as our high omega. So our high omega will not pass the low pass filter, and therefore we will not have any value for our V out of the whole cascaded circuit. Now, for a low omega input it into the low pass filter, it will pass the low pass filter because it's a low pass, but it will not pass the high pass filter. Therefore, we will still not get any voltage for our V out. That means we will only get V out, which is almost equal to V in, if our voltage, our frequency, is less than the low pass filter cutoff frequency and greater than our high pass filter cutoff frequency. So any value less than the cutoff frequency of the high pass or greater than the cutoff frequency of the low pass, mainly when our omega approaches 0 or our omega approaches infinity, they will give us 0 voltage. So finally, we call this a bandpass filter. I hope that makes sense. And see you on the next video on question 4.